What's up, you guys? Welcome to Integration Bee Training for Advanced. This is 12.4. So we are finally going to learn how to do piecewise integrals by summation. So let me go ahead and show you how this concept works. So if you remember before, right, how piecewise integrals like the floor function and the ceiling function, they're all like the way the graph looks like. It's like in rectangles pretty much when we integrate the area under the curve. Well, not really a curve, but here, when we integrate floor functions or ceiling functions, they look like this in a bunch of rectangles, whatever. So pretty much things like this. And whenever we have some function in terms of this, then you get some weird curve functions, whatever. Like let's say, like, assuming this function looks like this, then the floor function would be like this, but with integers or whatever. So, and when we integrate, the area under the curve is just going to be a bunch of rectangles. And so a lot of the times, because these are a bunch of rectangles and integers, a lot of the times it's easier and faster to put it in sums. So let's say for some function, if we have whatever, you have like functions, a regular function, and then you have some parts where it's a floor function or a ceiling function, or it could even have fractional parts, right? So things like this, you can actually turn it into a summation because, again, most of the function parts, they're just rectangles when we integrate them. And so what's going to happen is what this would look like is when we put it in summation form. Well, let me draw this in yellow. When we put it in summation form, we start with whatever this initial number is. If this was like a, for example, right? It doesn't always have to be 0. It could, most of the time it's 0 or 1, but for any number a in general, then the sum starts from n equals to a. And then if it was infinity, then we say infinity, right? I will mention this. If this was b, then this would be b minus 1. So that's something you do have to be careful with, is if it wasn't infinity, it's like an actual number, then on top you would put b minus 1. And the reason is because if you think about it, like from a to b, right, you have like starting with a and you kind of initially start counting. You go up to a, then to a plus 1, whatever, then you go up to b minus 1 here. And then you stop there because b minus 1 is already adding this whole rectangle here. Continuing with the infinity though, most of the times, a lot of the integrals that you'll come across, it'll just have infinity. Well, mostly because it's just nicer. So if this is infinity, then this becomes infinity. And then you integrate with n and n plus 1. So from n to n plus 1, and then this is f of x because it doesn't have any floor functions. So anything with a floor function, you turn it in terms of n. It becomes n because, again, floor functions is part of the summation. So now it's an n. And so for h, if it was a ceiling function, it's n plus 1. Does that make sense? So pretty much we're using we're turning these functions in terms of floor functions. So like this here, t, would now be x minus n. And so now this whole integral now looks like this. And n plus 1 f of x t of x minus n dx. And then you just integrate this part, and then at the very end you have to add on to these to compute the sum. And that's like the only reason why I hate piecewise integration is, sometimes you're given a summation problem rather than an integral. Okay? So now let's go ahead and dive into some examples. So because this one is just, it contains a bunch of floor functions and ceiling function, just a simple integral, we can turn this into a summation. So, if we follow, so what's our lower bound? We have 0. Our upper bound's 10. So this is 9. Okay? And so now we integrate from n to n plus 1. Okay? That's why we do the minus 1, because we're implementing n plus 1. And then here, now it's just n, and then this one is n plus 1. Oh wow, how easy. Everything's a constant. So n plus 1 minus n, that's just 1. So like I said, this integral is not really an integral. It's just a sum. That's all this is. Okay? This is very tedious. So I'm not going to actually go whatever. You can, though. You would have to know the sum of n squared and n. But when you do that tedious computation, you should get the answer 330. Okay? Yeah. Like I said, I hate piecewise integration because I am not a fan of sums. Okay? Again, another integral where it's literally just a sum. So because everything's in terms of floor functions, we can just immediately turn this into a sum. So at infinity, we have n equals to 2. So because everything's in terms of floor functions, it's just simply n minus 1 n factorial. That's it. Because everything gets converted into n's. And the integral from n to n plus 1 is just 1. So here, this is Taylor series. So I could actually simplify this for the sake of time. This is what? N minus 1 factorial minus 1 over n factorial, right? And so now this would, oh wait, I'm sorry. Oh no, we can leave it like this. Yeah, this is just simply 1. Telescoping, technically. This is more of a telescoping sum. Okay, that was quick. Alright, next integral. So we have a very intimidating looking integral here, right? Don't freak out. Breathe. Don't freak out. We're going to do the same procedure. We're going to sum it up, right? So a lot of the times when you see something like from 0 to infinity, that's where, okay, we can't, you can't do this manually. Otherwise, you're going to go forever. So that's why we use summations. So let's go ahead and sum this up. See what this looks like. N equal to 0, because it has a 0. From n to n plus 1. And now we have x minus n of n plus 1 dx. Okay. So we have x minus n. We can let u equal x minus n. And this is very nice because your bounds are now from 0 to 1. Right? Plug in n plus 1, you get 0 to 1. So now it's just u to the power of n plus 1 du. This is simple. When you integrate it, you get left off with the sum of n plus 1 square. Right, and if you plug it in for each term, it's simply the same thing as this Gauss sum it is simply the same thing as this Gauss sum, 1 over n squared. And so now your answer is pi squared over 6. And you're done. See? Again, summations, summation is very helpful to solve these integrals super quickly. Again, the only difficult thing is the summation part. Right now I'm just giving, a lot of the common ones are easy, but not every piecewise integration has easy sums. Okay, we have a composite piecewise function, sort of ish. Not too bad, because everything's in square roots. So again, you could literally just let u equal square root of x. And with that substitution, you'd be left off with, that's not 0, 1 to infinity. You get du to the square root. We have u and u square with the floor functions. Okay. And now, because everything's in terms of floor functions, you could just literally turn this into a sum immediately. So now this is from n equal to 1 to infinity. This is now, we could factor it out technically. It's just this. Awesome. This is telescoping series, very famous sum. The answer is just 2. Okay, and that's it. Ooh, interesting. Interesting. So, again, we immediately turn this into a sum, right? See what this looks like. N equal to 0, n to n plus 1. We have 2, that's a fractional part. So we have x minus n. And then we have 4 to the power of n dx. Okay. Huh. Interesting. We can actually simplify this a lot further. N equal to 0. Here, this 2 to the power of negative n can be combined. So we have, what? 1 over 8n. And then all I have to do is integrate 2x. Which actually, I'll write the whole sum again. So this would be like, we'll have ln of 2. Oh, no, it will be, I'm sorry, it'll be divided. Ln of 2 at the bottom, and then 2n plus 1 minus 2n. Okay, so that's our sum. 2 to the power of n, can we factor that out? I think we can. Yes. Right, factor 2n, 2 minus, oh, wow. Okay, well this is awesome. See, it cancels out very nicely. So now we're left with 1/4 n with 1 over ln of 2. So this is the geometric series. So our answer should just be like what? 4/3? 4/3 divided by ln of 2. So this should be our answer. Okay. Again, a lot of these integrals are they're always gonna look very intimidating. So the first step is to just turn it into a sum, and then integrate, and then see where things cancels out. Okay. That was our last integral. That's pretty much it for this. Technically, an introduction to summation with piecewise integrals. So I hope this was helpful. Again, it's very, very helpful actually. This can actually help you solve piecewise integration a lot faster. So, go ahead and replay this video and practice it yourself. Kind of get used to this whole piecewise integration concept. Okay? Alright, thank you so much for watching, and I'll see you guys in the next video.